Mohammad has worked with Bill in terms of working with the bone mineral density database, correct? And on nomination sampling techniques. And this is work that Mohammad has been involved in, and I know Olawale Ayalara, who's a PhD student that's co-supervised by Mohammad and myself, has worked in this area as well in his master's thesis research area. So, and Mohammad is a professor in the Department of Statistics here at the U of M and has a lot of interest in machine learning and large-scale computational methods. So we're pleased to have Mohammad join us today. Mohammad, we'll reserve questions for the end, and people can put them in the chat or can open up their microphones after the presentation to ask questions. That sound okay?
Yeah, absolutely.
Okay, I'll just monitor the chat function as we go through it. So Mohammad, I'll turn it over to you, and thanks so much for being with us today.
You're welcome. Okay, thank you everybody for getting up this early in the morning these days, I guess, and then listening to this talk. As Lisa mentioned, this is actually part of what I did with my MSc student, master's student, Olawale. And Bill was also involved. I've been working on, and I'm still working on, some problem related to osteoporosis, and this is one of the works. So I added a few things to this, work that Olawale did, and I'm going to present that part as well. So this work, part of this work that I'm presenting, is appeared in Statistics in Medicine in 2018. And the next part, which I'm working on, that will be submitted soon. So before I start, let me just talk about what I do. So this is a complex analytics research lab that I have it virtually. I don't have a physical location for that. And as you can see, I have a couple of students here and some of my colleagues working with me. And some of these people are actually graduated, and I didn't have time to update this and then put a new photo. But what we do in Carl, we develop new methods and use computational tools and a statistical method to understand complex data. And sometimes we also generate complex data because we believe that sometimes working with data in hand is not that beneficial, and you need to be clever to get more out of the data in hand. And what I do has several applications, and one of the major applications is in health science. So in summary, if I want to say my current research program, I do a lot of statistical, or let's say machine learning techniques for data-driven problems. So these are some of the problems that I've been working on recently: calibrating a smart forceps in neurosurgery, which is with a NeuroArm group in Calgary; deep learning for personalized medicine using medical imaging data, or using regularized models and also random forest models for screening obstructive sleep apnea using breathing sounds. This is with biomedical engineering. What I'm going to present is on my second actually area of research, which is tied with the first one, and it's called target sampling based on ranks. And it has many applications in medical research and in fisheries, environmental studies. I've also done a good amount of research on small area estimation with measurement errors. So these are my main areas of research currently, but my main focus mostly is on the first direction at the moment. So let me just put this here. Okay, does it work? Okay, yeah, it works. So let me, how can I move this? Okay, sorry. Should be a way to move that to the other side, but it's not working. I'm going to actually present a little bit about Manitoba Bmd program and the current method for BMD analysis. BMD actually is used for bone mineral density. And I'm going to talk about the proposed method that we have. So Manitoba Bmd program, Bill should talk about this because he's more familiar with, with this than me. What is osteoporosis? It actually is a disease that happens when a person experiences significant loss of bone density, and bones become kind of more fragile and prone to fracture. And the word osteoporosis means Paris bones. So in this graph here, or this figure here, you can see that the these are different stages of, from healthy person to osteoporosis over ages. And here it shows, you know, an example of a very healthy bone, which is very dense. And this one actually shows a bone that actually lost lots of its density and is more prone to fracture. This disease, it's known as a silent thief because bone deterioration can happen over a number of years without showing any symptoms. And then the fracture happens. This fracture, usually they are very common in hip, in spine, in wrist, and shoulder. And people who live with osteoporosis, they face a reduced quality of life. They might lose mobility. They might depend on other people. And in some cases, it might actually cause death. About 28% of women and 37% of men who suffer from a hip fracture will die within the following year, unfortunately. So that's a very serious disease. And as you can see here in this graph, you can see that we gain bone mass up to an age. So let's say here about 35, okay? So up to that age, we gain actually bone mass. And after that, we start losing a little bit of the bone mass over time. And this drop is severe for female actually than men. As you can see here, it has a, you know, a sharp slope here. And this is just examples of the fractures, a sketch of the fractures, let's say here. So some of these numbers might need to be updated. So I borrowed them from the previous talk that Bill gave, and also some of the literature review that Olawale provided in his thesis. So I don't know how updated these numbers are. Bill can correct me if I'm wrong. Let's talk about the prevalence of osteoporosis and its cost. You might all know because I've seen a couple of talks about osteoporosis, but to just make sure that for those people who recently joined the group, you have some ideas about what's going on. This is a most common disease among people of age 50 and older. It's estimated to be a major public health threat. 2 million Canadians are affected by osteoporosis, essentially. And at least 1 in 3 women and 1 in 5 men will break a bone due to this disease in their lives. The annual cost is also very high. In 2011, the cost for, you know, taking care of people with osteoporosis or diagnosing this disease was about $4.6 billion, which is a large number. And researchers believe that costs will double during the next 30 years unless you have comprehensive programs for screening, prevention, and treatment. And as you can see here, this is just I assume it's an old graph that shows the incidence of osteoporosis fracture compared with heart attack, stroke, and breast cancer. We are all afraid of these diseases, like heart attack. But if you look at the total number of people, who have this disease, and compared with other one, okay, that are more famous than other, osteoporosis, and people are, know them, you can see that osteoporotic fractures are more common than heart attack, stroke, and breast cancer combined together. So, there's a hope, and the good news is that we have different programs to combat this disease, okay? And the famous one that I'm aware of is Manitoba Bone Mineral Density Program, Mbdp, and this is their website, and they give you a lot of, good information, useful information, and different strategies, how to self-manage if you have this disease, and what you need to do. And this is the link that I provided here. This program was developed to combat this major public threat, and they regularly collect information about the population at risk. These are the only provider of clinical bone densitometry service to the region, and they define usually the optimal timing of initial and the follow-up measurements. They have the largest population-based database of BMD analysis. They started in 1990. And completeness and accuracy, they have a very, complete data set, and the accuracy is high. So some of these things might not be completely right. So hopefully Bill will correct me. Okay, so that's an important disease, but how should I diagnose for osteoporosis? There are standard ways to do that. You need to see a doctor, and then if doctor is suspicious that you have this disease and you have some, family history and things like that, they'll ask you to go and then perform an X-ray, which is called the DEXA scan. It's a dual energy X-ray scan. This is easy to use. It actually has low exposure to radiation, but it's costly, rather costly. And when they get this measurement, doctor will actually, let's say, obtain something like that. They do this, scan like that. They do measurements, and depending on the area, they can actually obtain a score for you. And then after that, they obtain a BMD measurement. They compare it with, let's say, this is just one way. You can obtain a couple of scores. This is a T-score. They compare a person bone mass with an average young adult of the same gender, and they have a T-score. And now the rest is similar to what we do in a normal distribution or T-distribution, that we are looking for extreme values. If you say this is let's say a T-distribution, then up to minus, let's say 1 is considered as normal. This is considered as normal. If your T-score is there. If you are in this region between -1 and let's say -2.5, you are at risk of having or developing this disease. And if you're in this region, in the tail, they tell you that you have the disease. Okay, so that's the whole story, more or less, about diagnosing this. There are a lot of things into that which I skip here. But for me, as a person who wants to analyze the data, I thought this amount of information is enough to be able to understand, okay, which area is important, what type of a score is important for me, and so on. So what is the current method to do BMD analysis? There are many literature in this area, and people are using very simple methods to very complex methods to analyze the data that they have. More or less, a common part in the current methods involve studying the relationship between, let's say, the BMD, bone mineral density, and some easy to obtain covariates, such as age, gender, BMI, body mass index, and family story, smoking status, things like that. Okay, but not only the relationship between BMD and these covariates is important, usually regression analysis is about how the mean of the variable, response variable, is changing with other variables. But here, we are not interested really in the mean, okay? We are interested in how the tail of the distribution is changing. For example, I want to see those people who have low BMD, which are located on the tail of the distribution of the BMD, how this tail is behaving with these covariates. And can I find an easier way to predict the value of BMD, for example, and using those easy to obtain covariates? So that's one of the goals, and you might be interested in studying the conditional tail behavior of the BMD. So that's the first question. And understanding how covariates will actually influence the tail of the conditional distribution of Y is important in many applications, not only in this problem. So why I chose this problem is, first of all, it's relevant. And since most of us are interested in applications, you can use the method developed here for other applications, such as risk analysis, such as medical research, such as environmental studies. Some people, they might say, okay, your concern is that the distribution of the BMD, let's say, is highly skewed. Okay, it's like that. Then I will actually, I might use median regression, because when it's highly skewed, first of all, the model will be affected by outliers, because that means you have a lot of outliers. So I use more robust method like median regression. Okay, yeah, you can do that, but still you're not getting information about the tail of the distribution. So you can actually use median. Some people say, you know what, I make a transformation. These are the current methods. I make a transformation on your data. For example, it's Y. Then I use a G of Y, and then I change it to a symmetric distribution. When it's symmetric, then I use, again, the current methods. First of all, median regression is a good, let's say, alternative to mean regression where you're working with data like BMD. Some people, they just use regression, but that's not, advisable, or I don't recommend that because of highly skewed distribution of the BMD. I don't also recommend using this transformation, because when you make that transformation, then it's very hard to interpret the model, because you're not working with the BMD or the t-square, you're working with a function of that. So interpretation becomes very hard. So let me just go back to the problem that I talked about. So this is, let's say, the data set on a spine BMD. These are the BMD values, or maybe the t-score, or I think these are the BMD values, and this is the age. And as you can see that the usual, or let's say the first thing that comes into the mind to study the relationship between, let's just say BMD as response, Y is BMD, and X as, let's say, age. Maybe you want to say Y is equal to beta 0 plus beta 1 X plus epsilon. So that's the model, and this is what you get. But as you can see, what I'm trying to do here is that at each age level, then I'm trying to estimate, let's say, the mean, and then find the relationship between the mean of the distribution and X covariate. So that's what I'm trying to do. First of all, as I said, distribution of BMD is not symmetric here, it's asymmetric. And also, I'm not really interested in data. Maybe I'm interested in what's going on here. Or maybe I'm interested in what's going on there, okay? People with low BMD. How, and the way that this area is changing with age is different from the way that this area is changing with X. And as you can see here, for example, the overall relationship is decreasing, but when it comes to the area to the top here, the overall relationship is increasing. So that's essentially what's going on. The overall thing, or the regression, shows what's going on in the middle of the distribution. But when it comes to the tail of the distribution, the behavior that you see is not necessarily the same, and you have to be careful, yes? So how can I model the tail of the distribution and how it changes with X? The tool is quantile regression, okay? The quantile regression is used for that purpose. And this is the model that was actually introduced in 1978. So it's a very old, actually, method that is available in the literature. And the idea is that you write the quantile, this quantile here, as a linear function of X, okay? And the goal is to obtain this beta. So there are two problems here. In a usual regression, what we do, we say yi, I want to write it as, a model of X, is essentially yi as a linear model of X. So I do have access to yi because I go to the population and I get the data, yi. But when it comes to this model, the problem is that I don't know the quantiles. I don't have the quantiles. So essentially modeling this essentially is hard at this current. So I'm talking about something that I cannot observe because I don't have access to the distribution of y given x. I do have x's. I can write the right part, but the left part, I have no idea. So I need to find a way that when I can use my yi still. And when I do the modeling, when I look at, let's say, how yi is different from xi beta, when I actually look at this difference, by doing the optimization, I know that I'm actually optimizing the relationship between the quantiles and x. So for the usual regression, people use this loss function, or this, S-squared error loss. We are all familiar with that, okay? So that's essentially the loss function that I have. So what you do, you just take expectation of y minus x beta to the power of 2, and then given x, and then you try to minimize that with respect to beta. And if you do that, you can actually see that what you're doing, you can obtain beta, and at the same time, you are obtaining expectation of y given x. So you know that, let's say, y minus a to the power of 2, when you minimize expectation of that given x, this A is expectation of y given x. So essentially, when you work with the quadratic loss function, automatically, when you work with y, you're estimating the mean of the model. So that's what's going on. Can I obtain another maybe objective function, another loss function, that when I minimize that loss function, instead of getting the mean, I can get the quantile as an outcome. So that was the whole idea behind a loss function, which is called check loss function. Okay, the check loss function, which is this guy here, is different from squared error loss. So if squared error loss is symmetric, is like that. The check loss function, for example, depending on tau, could be, let me use a different color, could be this. Okay, so it could be that. So this is a loss function that I use, and I call it rho, tau, and epsilon. So this is tau epsilon, and this is 1 minus tau epsilon, let's say. Okay, or tau minus 1 epsilon. So that's the loss function. Why I'm actually talking about that, sorry if it's a little bit of, a little bit technical or it has math in it. It's good to understand that the idea behind defining the different loss functions is that each loss function, you can use it to target different part of the distribution, okay? Quadratic loss function, using that, you just target the mean of the distribution, and you try to model the mean as a function of x. But if your goal is not the mean of the distribution, then working with a quadratic loss function and the usual regression function is not suitable. So you have to work with this. If you look at expectation of, let's say, rho tau of y minus a as a function of x, then the best a that you can obtain is quantile. Tau quantile of y given x is the thousandth quantile of the distribution of y given x. So that's a good thing. So when we have that result, what should I do? I just say, you know what, don't worry about not knowing this part. Use your yi, find a set of beta such that this linear function is close to yi, but instead of looking at the distance using the Euclidean norm, use this rho function, which is an ugly function, but that does the job for you. Okay, so, but you can see that the function actually changes its behavior depending on positive error, overestimating, or negative error, underestimating. So that's why I write it as two parts, okay? So I have the first part when I'm, let's say, underestimating using my model, and this part when I'm overestimating. So I'm actually giving different penalties for overestimation, underestimation. And it makes sense because if I'm actually interested in the right tail, if my line actually directs me to the wrong direction, I should give more penalty. I don't want to actually get away from the area that I'm interested in, okay? And it's useful for me. Okay, so that's it. This is called the check function, and that's what people use in practice. Later on, people say, you know what? The check function corresponds to a distribution as well, because it's in like quadratic. Why Euclidean norm is important and why normal distribution is important? Because we all know that when we have yi minus a to the power of 2 over 2, and let's say this normal, and I have a likelihood, let's say, and I want to maximize that with respect to a, this is equivalent to minimizing summation of yi minus a to the power of 2. This maximization on the left is equal to minimization to the right, okay? So that's why the normal distribution and Euclidean norm or quadratic loss function, they're actually walking hand in hand. For the quantum regression, we have another thing, and that thing is called asymmetric Laplace distribution. So everything that you can actually obtain using a check function can more or less be obtained under the asymmetric Laplace distribution. So that's the correspondence. So if normal actually is tied with S-squared error loss, asymmetric Laplace distribution is also tied with quantum regression and check function, okay? Why this is important? Because now I can perform Bayesian analysis, I can do parametric models, I can do all the things that I have, and that makes things actually very easy for the life of a statistician. And when it comes to the asymmetric Laplace distribution, it has a CDF which is given here. The form is not important. I just want to say it's a legitimate, distribution, and you have some properties for that. Okay, so now that we learned about the BMD program, we learned about that, okay, I'm interested in the quantile or the tail of the distribution, how it behaves or changes with X. Then the thing is that, what is the current method in the literature? The current methods in the literature, in my opinion, most of them are not efficient, especially when you want to model the tail of the distribution. They're costly because they need to have large samples to be able to actually provide reasonable estimates. And they are not designed for BMD distribution, which is highly skewed. Okay, so what is the objectives here? The objective is that, is it possible to perform BMD analysis, especially for the follow-up study, let's say, what we are aiming to achieve in the future, with lower cost and obtain results that are comparable in terms of precision with the current method? Is it even better if we could, it's even better if we can do that analysis even cheaper? And how can I perform median analysis to make sure that my accurate results are robust? Okay, so the thing that we developed with Olawale and Leslie is actually the core of that, or the main idea is here. We want to use expert knowledge, okay? When I say expert knowledge, I don't necessarily mean talking to a doctor. I mean use previous data, auxiliary information, use Frog's score, everything that you can easily, or anything that you can easily obtain from the population to perform some kind of target sampling. And so essentially, it's like a purposive sampling, but in a probabilistic way. So what we do is that we first take a small number of individuals, and then we rank them based on historical data and identify those individuals who are more suitable for the study. And we call that a rank-based target sampling, okay? Suppose that I have K individuals, okay? We call it a set of patients. And we kind of use a map, an expert map, I call it expert map, which goes to this group and then say, among this K individual, this individual, call it U star I, is the one that's more suitable for the study. And then go and then take the data from this individual. Yes. So I'm trying to bias my data towards those part of the population, or those individuals that are more suitable. And I call this a nominee of UI. And then I collect a bunch of data this way, which we call it a nomination sampling. And this is exactly what people want to do in practice. But if you just don't do that randomization at the beginning, everything becomes purposive sampling, and there is no way that you can extend the result to the population. Okay, so if the target is the person with the highest chance of having lowest BMD, or maybe I look at the baseline study and I say among the baseline BMD value that I have, this individual has the lowest one. So I suspect in the follow-up, this person also has, a low BMD. So I collect that person. So this is called a minimum nominated sample. If I nominate the one in the middle, I call it median ranked sample. So that's what we have. That's my sample. Okay, so let's see how this is going to help me. Suppose this is the underlying population. So the black one here is the underlying population. And I'm interested in getting information or understanding this part of the data population. So if I take a sample of size, let's say this is a sample of size 100 from the black one, you can see it's essentially a very tiny small of the population that comes from my sample, that comes from this part of the population that I'm interested in. So I'm interested in this part, and you can see in my sample, I have a tiny bit of the data, okay, using the usual method that people use in practice. But now I take two individuals each time, and I rank them, and I take the lowest part. So what's going to happen? So I partition the data in my population in two parts, this part and then the other one, which I call it the blue one, this part. And I ignore the blue one, and I focus on the green one. Now what happened is that from that area, I have this portion in my sample. If I partition it even more, three parts, this is the proportion of people that I get. And if I actually do it even more, you can see that in my sample, I increase the chance of getting individuals from the areas that are more interesting. So if these are people at risk, you can see that the proportion of people at risk that I have in my final sample is increasing dramatically, okay? So that's good, because that means from that part of the population, I can actually get more information. You might say I can stratify the data and then get, so yes, you can also do that, but even in a stratified sample, you can perform the method that we propose, okay? So now this is good, but the downside is that the data is not simple random sample. The downside is that the data actually has a distribution which has this part. How should I incorporate this extra rank information, okay, into my analysis? How can I do that? I have to plug in my, I have to plug in my laptop before it actually is dead. So just give me a minute, not a minute, just maybe a couple of seconds. Okay, so how should I incorporate the rank information? There are different ways to do that. And what we decided is that we said we want to do non-parametric because we don't know the distribution of the BMD in the population. We don't want to assume anything about that. We're talking with about doctors. They don't want to make unrealistic assumptions. So we ended up developing a loss function that in the loss function, this is very similar to the check function, and that's the contribution of the rank, okay? That's the contribution. So that's what we did. Essentially, we came up with this loss function, and it's similar to the check function. And if k is equal to 1, that means if I'm doing comparison with only one individual, that means the usual simple random sample, this actually reduces to the check function. And when k becomes large, then that contribution actually is gone. We call it mean NS check function. And this is the way that it works. If I'm interested, let's say, in this tau, which is the left tail of the distribution, the usual check function is the solid black one. But in our proposed methods, what happens is that since we have data coming from the right side of the distribution, okay, the side that we are interested in, we actually give less penalty to the error that they are making because they're coming from the right area. So we give them more time to talk because we know that they're coming from the scene. Okay, so that's the benefit of the loss function. For the median rank sampling, this is the new development that I have here. We came up with this, this loss function, and then we could. It's a little bit of technical, but we could simplify it to actually kind of obtain something very similar to absolute value, which is used for robust regression analysis with some extra term, and that's the contribution of the rank, okay? So these are the contribution of the extra information. So that's a naive way to use that information. Okay, and as you can see, since the data are coming from the middle part right now, okay, I give less penalty even if I make a mistake because the data are coming from the right part, okay, I let them talk. And that's why I let them to make mistakes, but since they're coming from the area of interest, the error that they're making is not that severe, so I give less penalty. So that's the comparison of the usual or the loss that we introduce and the usual loss function. Okay, and the only difficulty is that this loss function that we introduce here are more complicated, but and then computationally you might say, okay, it's harder to optimize, but the usual method that people use for check function is applicable here. So you just need to modify the target function, and the machinery that people use already in practice can be used here. And you can use M estimation approach. You can use the NAG, Nesterov accelerate gradient, method for doing the optimization, or recursive methods that I'm not going to go through the details. If you're interested, I can explain it later on. But now this is the method. Let's see how it performs in practice. So the goal is to predict the lower tail and the central quantiles, let's say, of the distribution of the follow-up BMD measurement of women using baseline information. So I have the baseline data. I want to see what's going on in the follow-up, okay? But I don't want to examine all the individuals. I want to say because it's a follow-up study, or maybe something that, or small studies in between these, timelines. And I want to monitor the population. I don't want to spend, lots of money. I want to get a small sample, but more informative sample, because I have a tight budget, for example. So I have a data set here, and I have a population consisting of lumbar spine, femoral neck, and total hip measurement of about 10,000 individuals. These are the characteristics of the data that we have. And for example, the average age, the weight, average hip fat, and let's say spine average fat, mean BMD. And then we did a cross-sectional study. We divided individuals into different groups. Those that we have the follow-up, or their follow-up is obtained between 0 to 3 years, 4 to 5 years, and then more than 5 years. And so this is what's going on in the baseline, and I'm interested in the first follow-up. So I use the information here to predict what's going on there. I know the truth, then I can actually make a comparison. So what did we do? We took a sample of size 200, let's say, very small sample, using the usual method and using what we proposed, for example. And then we are interested in estimating different, X spectrums of quantiles here. And we predicted let's say, the BMD or the T-score and Z-scores for the individual in the follow-up, and then we compared with the truth. Let's see what happens. This is the precision or relative efficiency that we got, okay? When we are estimating the quantile, the tail of the distribution. And let's see what happens. Depending on which variable I'm using for ranking and how this is done, the efficiency gain is significant, okay? Let's say if I'm interested in, let's say, quantile 0.2, a value that 20% of the people actually having a BMD level less than that, the precision actually ranges, depending on which category that I'm talking about, ranges from 5 to 15, which is a huge increase in the precision. Sometimes it goes even to, in some cases, to 16, 17. But when I go to the tail of the distribution, even in, let's say, if, I don't know, if I'm interested in here, the precision goes up to 15, 10. But when I go to the even more extreme tail, that's hard to reach, or rare population, the efficiency gain becomes actually huge. And in the median also, the improvement, because median is a place that the data is abundant, okay? I have a lot of data. SRS already does a good job. But in this case, you can see that using the proposed method, the efficiency increases by a factor of 5 sometimes. So even in an area that you have a good amount of data, you can actually do a much better job using this method. And in terms of the cost efficiency, you can easily see that. Suppose that the EXA image costs $125 per person. In a simple random sample, if I take a sample of size 200, that means I have to spend about $25,000 to collect the data, okay? And these are the errors that I'm actually encountering in the analysis. I do the same analysis using only 40 data points, which means I'm spending $5,000. And let's see what happens. The error here is 0.0081. Still, I'm doing better than that. The error here is 0.0078. Still, I'm doing better than that. Okay? So, and when it actually, the efficiency, it becomes even more when you go to the more extreme or rare population, rare part or hard to reach part of the population. So the financial implication of this is immediately apparent. So essentially, the method not only provides a better estimate, but also is cost efficient. Okay? So that's what's going on. But how can you explain the best or the good performance of this method? And how do you choose about the set size K? How many patients should I compare? We have a formula for that, okay? And let's just see what happens. Suppose that this is the black one here, this guy here, is the original population, and I'm interested in this value. So this value obviously is a tail quantity for the original distribution. When I start doing nomination sample, let's see what happens. So I said when K is 2, I divide the population in two parts. So that's one part and that's another part. And I ignore the red part. I'm focusing on this left side. So what happens? Something that is tail for the blue one is not tail anymore for the induced population. And if I actually increase K, let's say K is equal to 5, what happens is that something that was tail for the original population all of a sudden became median for the new population. And I know that I can get the best performance for the median using, quantum regression. So that's why essentially the nomination sampling, what it does for you, something actually it transforms something that is tail, a tail quantity for original population, it actually transforms it to the median for the new population or induced population, and you have the best performance there. And you can actually find that case. So here in this graph, we showed that, the maximum happens at somewhere. Where's K that the maximum happens for each? What is the value of K? We can, using this correspondence that I just showed you, we can obtain that K. And that K actually is this formula here. So this ugly formula here essentially is obtained because of the correspondence. That's something that was, let's say, the 1000th quantile for the original population. It's not 1000th quantile, it's something like that. And then I say, you know what, this quantile in the induced population, how can I choose K such that this guy becomes median? Because I know the best performance happens at the median. Solve for K, and then you can see K becomes this 1 minus tau. So that's essentially what's going on. And this is just part of the result that we have. For more information, you can actually look at the paper with Olawale and Bill Leslie, and then I will upload a new draft that explains how you can extend this to median and other quantities of interest, and more development will actually come soon. I think that's all I wanted to talk to you, and then just, give you some information about, if you change your perspective from selecting data, you can actually get a lot of useful information and develop more precise methods to study, an old problem. So that's it. I guess I'm done.
Well, thank you very much. Thanks for explaining the paper that I'm a co-author on and contributed so little to. It's very, very interesting and very clearly articulated. So much appreciate that. I'm sure that there are going to be some questions about where else you're planning on applying this method. Maybe I'll launch in with that question while people are formulating their questions. What other data sets are you looking at using this procedure for?
This target sampling, Scott is actually trying to use this in image processing and deep learning, and see whether we can actually, there are a couple of actually ideas that you can expand, because we have this pooling, let's say, stage in deep learning. And in the pooling, people decide arbitrarily what to select. For example, max pooling, min pooling, these are all just target sampling. One of the ideas is how you can actually perform a pooling, an efficient pooling, let's say, in deep learning. The other thing is that when you do deep learning, you need a lot of label data. Can I use the benefit of this method to obtain, a more efficient approach that without actually taking millions of images, maybe with 100K of label images, I can actually gain the same precision. So that's another application. So I'm trying to tie this with a more modern techniques, and then, create new creatures that are efficient in practice. And so that's it. And in terms of, because one of the things here is that how you perform ranking. One thing that I'm investing is that how can I provide more efficient ways of ranking and then bringing that information into the analysis. So that's another direction. There are a couple of, directions that I'm working on right now, or my students are working right now. Yeah.
Thanks. I'll open it up. Any other questions? Feel free to jump in. Well, this talk just reinforces my view that bone density is a metaphor for life.
Yeah. Yeah, sorry if it was kind of I intended not to have, mathematics in it, but I thought it's good to see the whole process of, having a crazy idea at the beginning and then developing a tool for your idea and then showing how it performs in practice. So this transition we're going at, I think it was a very interesting experience with Wally and Bill, and we got a lot of insightful comments from Bill as well. So although he was so modest to saying that he didn't contribute, but he made lots of good comments.
I'll ask a question, Mohammed, in
Yeah.
terms of figuring out which quantiles you're going to focus on in your analysis too. Can you talk a little bit about how those decisions are made, both from an empirical perspective, and also then I guess when you and Bill were talking about this also from some clinical perspective.
Yeah, there are two things here. Sometimes somebody tells you that I'm interested in this quantile, okay? For example, in a BMD analysis, you might say when the t-score BMD is 0.73, that's a cutoff. And then this corresponds to, I don't know, quantile 0.2. So sometimes a quantile is given to you. Then your job or my job is to find how many individuals should I compare to make sure that I'm in the right direction. So we have a formula for that. So if, for example, let me just go back here. For example, I might say, you know what, if tau is equal to 0.2, that means K, the set size, the number of people that I need to compare is between 1 to 5 people, okay? At most 5 people. And then this is the range. And then you say, okay, what among these 5 potential K, which one is the best one? You say the best one is this. Okay, you go for that, and then you obtain that K. So essentially, we give a method to obtain the best set size on the number of individuals that you need to compare. So that's it. The other thing is that you need to also know that sometimes the K is given to you because you say, you know what, the doctor or whatever method that I have for ranking is not able to rank more than 4 people because ranking becomes hard. Then that's a limitation. So it depends from what perspective you're looking at. If you are talking about administrative data, for example, that you don't have any limitation, you can just go to the data, take a sample, and then rank them. You can take K to be very large. For example, if you're interested in tau equal to 0.005, very rare part, okay, very hard to obtain, then you can take K in administrative data to be 15 or 20. But if you want an expert or some doctors to, let's say, to rank the data based on their appearance, then of course they make a lot of mistakes when it comes to more than 5 or 4 people. So you want to take K to be small. So yeah, it depends what the problem and who is actually initiating the problem.
Yeah, yeah, and I guess pointing out when you're working with clinicians, for example, that the association, as you've said, amongst your covariates and your quantile can be different depending on which part of the distribution you're looking at.
Yes.
So the relationships can be quite different.
Yeah, that's absolutely right. Yeah. By the way, one of the things is that you can actually use this setting in high dimensional data, whatever method that like lasso and things that people develop for, regular regression, you can use it here. And that's another area that, I'm currently also working with my students on that.
Mm-hmm.
Yeah.
Great. Other questions that people have or comments that they'd like to make on the method?
So, Mohammad, this is the Punjab. So, thank you for the talk. So, to my memory, there's some kind of a discussion or concerns about the estimation of quantile and or quantile regression. Now, concern is about reliability of this estimation. So, people say usually, so the quantile estimation, the reliability is quite kind of a low, especially when you go to say 90 quantile or 95 quantile. So I'm not sure how do you think about so whether so methods you mentioned here that will so improve the reliability of the quantile estimation or quantile regression, or still it's so basically the reliability is low when we get people often like kind of a 95% CI of the estimation, it's too wide, right? So whether that kind of a thing here can get improved.
Yeah, yeah, you're right. Actually, the whole idea here is to show you at the end of the day that the current method in the literature is not that reliable when it comes to you know, the tail of the distribution. Let's say tau is 0.05 and you have a population of size, let's say, I don't know, 1,000. If you just get a sample, if let's say 10,000 or 1,000. So what does it mean? It means that out of these 10,000, only 50 of them are sitting here, okay? So in the population, you have only 50 people that are there. And you want to actually get information about those 50 individuals with just taking a sample, let's say, of size 100. Okay, if you take a sample of size 100, what does it mean? It means that out of those 100 individuals, the current method will give you a sample of size 5. So out of those 100 people, only 5 of them are from that area. That's why the estimate is not reliable, because you're not getting information, that much information. So 95 individuals will give you information about other parts of the distribution that's not useful for you. Only 5 people out of those 100 give you information that is suitable. The current method, what it does, it increases the number of individuals that you get in your final sample, okay, from that part. And also it reduces the chance that you get individuals from the area that are not relevant. So it has 2 parts. Increases the chance of getting individual from this part that is relevant, reducing the chance of data getting from this part which is not relevant. That's why you see the efficiency increased by a factor of 15. Efficiency, you know, or increasing in the efficiency in the usual rank-based method are usually about, you know, 2 or maybe at 20%, 30%. If you're lucky, maybe 100%. Yes, but in this case we have 1,500 essentially. So that's 15, you know, times better. Why? Because we're talking about an area that the usual method, they cannot obtain data from that, and we increase the chance. But you saw that when I talk about the median, I don't see the improvement of 15. I see improvement of, let's say, 3 and 4. Okay, so that's why I say when you want to talk about the quantiles or rare population or a hard to reach population, then using nomination sampling or target sampling will actually increase the efficiency.
Okay, makes sense.
Yeah.
Any other questions?
Okay, you can always send me an email if you have any question, or when you look at these slides again and then some part is not clear, you can send me an email.
Yeah, so Allison's, we'll have the slides and recording, so thanks. All right, well, thanks, Mohammad. Thanks for joining us today.
You're welcome.
Thanks to everyone for participating today. We've, as we mentioned at the beginning, we've got a hiatus for July and August. If you have interest in presenting to the group, then we will resume in September, and we'll be glad to hear from those who might like to give a presentation.
Okay.
Bill, anything else to add?
No, just wish everyone pleasant summer, all the best. We looking forward to speaking with you, seeing you maybe in person, not remotely in the fall. That would be nice.